In this lesson, we'll look at continuity and some high maintenance friends. And by friends, I mean functions we can use in the real world to model physical behaviors. So remember, two pillars of calculus are limits, it's like Stonehenge, and continuity. And we rest calculus on those two. And calculus is generally thought of as having derivatives and antiderivatives at this level. So we've looked at limits, and we looked at limits with rules, and we looked at limits by mental powers. That's looking at graphs. We're going to do the same thing with continuity. We're going to start with pictures, and then we're going to do rules. So first, let me just introduce some of our high maintenance friends. If you haven't had much time to study these in other courses, sometimes these are left off. But absolute value functions, where you have x and some absolute values, and maybe it's 2x minus 3 in there or something. But they always look like a v, or sometimes they look like that. So it's always some kind of v or upside down v. The other one is step functions. And this guy here, you can see these little, and sometimes they do something like they'll have, oh, it's open there and closed there, so that it's defined everywhere. And what's going on here. And then this thing I'm calling Frankenstein's, where you take two functions that look different and you just kind of stick them together so that you cover the whole x-axis. Like there's something, if you pick an x, there's something that it'll find for a y in the map there. If there's an x, if x is over here, it'll find that. So do these fit the definition of functions when I call them friends? You can see anywhere you draw a vertical line, this guy will, even though it's maybe a little strange with that hard point there, like you don't want a young child near this function, but certainly passes a VLT. The vertical line passes, so it's a function. The same thing here. It's kind of off-putting that it jumps like that, but that's where we're at. And then this thing here also may be off-putting that it jumps, but anywhere you draw a vertical line, it'll only hit this guy once. And here you can see I've got a hard dot there and an open. So if you just happen to pick the vertical line here, it would be right this point. And if you go a hair to the left of that line and draw another line, it'll be down here. So I just call them Frankensteins. Sometimes these Frankensteins will line up, and you'll have things that are like piecewise. They call it piecewise continuous. So anyway, so I call them Frankensteins, whether they line up or not. And loosely, we say a function is nicest if it's smooth and continuous. And continuous means you can draw it without lifting the pen from the paper. So if you look at this one up here, this first one, you can draw it without lifting the pen. This one here, you have to lift the pen, so it's not continuous everywhere. This last one, you have to lift the pen once to draw. But continuous functions like this first one can be pointy. See that little point there? You could hurt your head. And that's why we bother saying they need to be smooth and continuous to be really good functions. So let's look at a few. This guy here, here's one. Here's a typical cubic. It's continuous. Can draw it without lifting the pen. Here's one that's not continuous. You can see I hopped there. And then here's one, even though it's pointy, I didn't have to lift the pen off the paper. And if you want to figure out if this is continuous, not by just inspection, if you want to really prove it, then you have to answer three questions. Is this graph of function f? Is it continuous at the point x equals 2? So there's the point where x is 2 and the y is we don't know. First you say, is f of 2 defined? Then you say, does the limit as x goes to 2 of f exist? And then, are the things from 1 and 2 the same? Let's see if I did that on the next page. Let's try it on this one. So if you look at this function at 2, you say, is f of 2 defined? Yeah, if you plug in 2, there's the y value. If you evaluate 2, there it is. There's a y that goes with it. So yes, is the limit as x goes to 2 of f of x is this. So as I go towards 2 here and I look at the altitude of the drone, you can see it's getting closer and closer to here. And then if I go to 2 from the left side, you can see the altitude gets closer to that same point. So from the left and the right, they both get to that point, and the height is, I have y written there. So yes, the limit exists. And then are those two the same thing? Yeah, this point where they both meet is the same as if I just plugged it in. So I would say, yeah, the limit, obviously from this picture, exists. at that point. So are the following continuous? Is there any, just use those mental powers again. So if you draw this, that looks continuous everywhere, so yes. How about this one here? You can see that little circle. That means we hop over that point. It's a bad point, so we say no. And then that third one, this is something from electrical engineering courses, but if you see this thing, you'll be like, oh, looks kind of weird right there, but I didn't have to lift the pen, so we say it is continuous, because I did not have to lift the pen off the paper to make those. So here's one where we have the rule, not just a picture, where we want to find where the point is discontinuous, or where it's not continuous. You might say, well, Parrish, I don't even have a picture. How am I supposed to know? Well, I mean, you could graph this thing by using a chart or something, get an idea. But most importantly, I think you need to realize that it cannot be continuous if it's undefined. So basically what we're saying is, can you plug everything in here and square it? Is there anything you can't plug in and square? It's a domain question in disguise, even though we're asking about continuity. We're asking, do we do any division by zero? And we're asking, is there any square roots of negative numbers? Those are the two things to look for. So right here, is there any division by zero? No. And 2, is there any square root of negative numbers? There's no square roots. So there's no division and there's no square roots. So no. So it's continuous everywhere. This one, is there any division? Oh yeah, x cannot be 0. And how about 2? Is there any square roots? No square roots. So here x cannot be 0, so it's discontinuous at x equals 0. That's what it's asking. Are there any points of discontinuity? And if you graph this guy, it looks like this. You can see I draw over here. I have to lift the pen to come down here to draw the next part. Where do I lift the pen? Where x equals 0. How about this one? What's bad here? No square roots. So we're only interested in division by 0. So we want, if x plus 2 is 0, we have division by 0. We'll just solve that little guy. So it's discontinuous at x equals minus 2. And you can write it like that. This guy here, e to the 5x minus 1. Oh, that last one had a graph. Looks something like this. Something like this. So you can see at minus 2 there's a problem. Then this guy, I'll just grab the graph for you. Looks something like this. It's continuous everywhere. And e to the power is a friend, is a good friend. It's a low maintenance friend. So I'll show you those high maintenance friends. I'll show you some other low ones on the next page, I think. And then hinge points. This is something that's sometimes skipped by algebra teachers. So if you're a little weak on this, no problem. Hinge point. We look at these guys, and in each of these, this doesn't have any divisions or square roots. This doesn't have any division or square roots. So we're only interested in the hinge point. So we plug 1 in. And what we're trying to check is, we're trying to see, is it this is a Frankenstein. This is what a Frankenstein looks like. Is it this one? Or is it this one? Does the bolt, did they put the bolt in before they connected the head to the body of Frankenstein? Is it discontinuous or continuous? And the way to do that is you just check that this guy has the same answer as this guy by plugging in the hinge point. Call it the hinge point right here, which is 1. So plug 1 into, so we have x and x squared are the two formulas. Plug 1 in, we have 1. We plug 1 into that, we have 1 squared, which is 1. And then you look at them and you say, oh, are they the same? Yes. If they're the same, then it's continuous everywhere. If you said, are they the same? And there's 1 and maybe that was 0 or 2. Then you say no. Then you say discontinuous at 1, the hinge point. Pretty simple, right? And this guy here, this is an absolute value, and they're kind of high maintenance, but it's just this 1 point. It's because the derivative isn't there. But this guy's actually pretty friendly, so we'll go ahead and say it's continuous everywhere. There's no division, there's no square root. And so let's try another round of this. If you want to sketch the graph of this kind of complicated function, it says, is f continuous at x equals 4? You can do this this is called by the definition, or at least the table, using tables for the 3 rules of continuity, not really by the definition. So if we want to find this limit, if it exists, we can use tables. We can take the limit as x goes to 4 from the right, and the limit as x goes to 4 from the left, right? Because we're interested at x equals 4. So here are the, dollar, dime, penny, thousandth, did something like that. So in this case, if I plugged it in, I would get, I think 8.1 and 8.01 and 8.001. So those definitely get closer to 8. And if I did this one, I'd get 7.9. I'll leave you to do the arithmetic if you want to play with the fraction. But if you see how you can algebraically manipulate it, you can see where I'm getting at. And so these are definitely getting closer and closer to 8 on both of them. And it's the same, so the limit exists, and the limit is 8. So yes, it is continuous at x equals 4. And some people will often write this little gem here, x minus 4. You can write that as a difference of squares. And then you do a little cancellation, and you end up with x plus 4, which makes filling this table out really easy. But you have to remember, even though the limit exists, you still can't plug that in. Oh, I'm sorry. I did make a mistake. No, it is not continuous at x equals 4 because 4 is not in the domain. So even though the limit exists, you cannot plug it in, so it fails that first rule. Oh, there it is, right here. I guess I should have read this. There we go. And then that's a pretty easy way to do it. If you want to graph it, it's x plus 4, so you would just at 4, 8, we'd have our hole. So you can see, even though there's a hole there, we can't plug in 4 because you can't divide by 4. It looks a lot like y equals x plus 4. And let's try some conditions of continuity to see if f is continuous at 5 for some different functions. So f of x equals minus 2. Let's sketch the graph of that. Y is minus 2, so it's this guy. You can see, is that a function? Yes, passes VLT. Is it continuous? Yes, I can draw it without lifting up the pen. So is f of 5 defined? So where's 5? 1, 2, 3, 4, 5. There's 5. And the function value of 5 is, there you have 5 minus 2 is on the line. So is minus 2, yes. It's defined. F of 5 is minus 2, so check for the first one. And does the limit exist? Well, you'd have to look at the limit. As x goes to 5 from the right, and the limit, yeah, I know, as x goes to 5 from the left. We make our little tables. This is the hardcore way. Some of you are visual people, and you're saying to yourself, visually I see it works, but I'm going to do this the hardcore way. So 5 from the right, 6, 5.1, and 5.01. Those are going to 5. And from the left, 4, 4.9, 4.99. Those are going to 5. And then we just plug it in. So what happens when you take f of 6? What's f of 6? This is such a dumb function. It just gives you minus 2 no matter what you plug in. So f of 6 is minus 2. What's f of 5.1? Minus 2. What's f of a banana? Minus 2. It doesn't care what you give it. It's going to give you minus 2. Same thing here. 4 minus 2 minus 2, minus 2. You might say, are those limiting to something? And the answer is yes, they are limiting to minus 2. And it's in a trivial way. It's so easy, it's hard for many students to get this because they're already there. It's like saying, is it going to be at Walmart tonight? And I'm like, yes, it's going to be at Walmart. It's already been at Walmart all day, and it's got a flat tire, so it's not going anywhere. It's always going to be there. So it's the same with minus 2 here. And so both are the same, so the limit exists. So yes, it exists, and it's minus 2. So is that's this one right here, minus 2, is that equal to this? That's this one up here. I say yes. So it is. So so f is continuous at x equals 5. That was a lot of work, right? Okay, and this next one here, 3x plus 2. So again, you do a. Can you plug it in? F of 5. 3 times 5 plus 2. That's 15 plus 2, 17. And then, so yeah, does it exist? Yes. And then the second part, does the limit exist? Limit is x goes to 5 from the right. Limit is x goes to 5 from the left. And we plug them in. So from the right, 6, 5.1, 5.01, 4, 4.9, 4.99, and then plug that in. So 6 times 3 is 18, 20. 5.1 times 3 is 15.3, so 17.3. And I think that's 17.03. So you can see those are getting closer and closer to 17. And then here you'll get some things, and you'll see that they get closer and closer to 17. So are those the same? Yes. So the answer to B is yes, the limit exists. And then part 3, or C if you want, or 3, are they the same? Yes. 17 is 17, so F is continuous at 5. Got another one here too. Why not? So here we have A. Can we just plug in 5? 2 times 5 squared minus 1. So 2550, that's 49. So yes, that works. And B, we have to do our little, this bit. Set it up just like before, just to look at some examples. And so 6, 5.1, 5.01, 4, 4.9, 4.99. So plug it in. 2 times 36, 72, 71. 5.1 squared, I might have to do that one. Times 2 minus 1 gives me 51.02. And then if I take that next one, 5.01 times 5.01 times 2 minus 1. So I get 49.2002. So anyway, if you do a couple more of them, you'll see those are getting close to 49. And the same down here, you'll see that we're going to get to 49. I'll leave that as an exercise to the reader. And they say, hey, A, B, I should be 1 and 2. But the part 3 here, are they the same? Yes. So F is continuous at 5. The other thing you could do is you could just kind of look at these formulas and say, well, is there any reason to think it's not? Like, is this minus 2? Is there any division? There's no division. Is there any square roots? No. So it's continuous everywhere. Therefore, it's continuous at 5. But this is the by the rules method. And then this is a line. Is there any division? No. Is there any square roots? No. So it's continuous everywhere, really. And then this one, same thing. Is there any division? No. Is there any square root? No. It's squared, but not square root. So we don't have to worry about any of that. So you really could argue it that way. So it's continuous everywhere, therefore it must be continuous at 5. And then we have a couple more here. So this one, let's try the first part, plugging it in. 1 over or f of 5. Let's evaluate it. 1 over 5 minus 5. Well, that's 1 over 0, which is undefined. And so that's an x. As soon as you get an x, you say f is not continuous at 5. But you could have looked here and said, well, the domain doesn't include 5, so it can't be continuous there. And same thing here, if you just look at this one, you say, we have problems. F of 5, this is, I guess, what I was calling a, or 1, is 5 squared minus 25, or 5 minus 5. And you could get into a chicken or egg question in your head, like, which do I do first? What is 0 over 0? What does that mean? And the bottom line is 5 is not in the domain. Therefore, f is not continuous at 5. So on this one, it's going to be a little tricky. But if you understand that there are multiple ways to look at it, you can look at the graph, you can look at the domain, and you can do these 3 rules. And it just depends on which textbook and how crazy they get over those kind of things. So you might also be wondering, just to finish up here, that since there's these high maintenance friends that make us to look at limits and continuity all the time, are there any low or medium maintenance friends? And yes, there are. And they're low maintenance friends. The ones we want to be around and invite to our party are linear functions. They're so sweet. A line, is it a function? Yes, look at that VLT, it's so easy. Does it have, is it continuous? Yes, it's so simple. And then we can figure out the slope and we know everything about it. And it's a pretty good estimate of things. And sometimes people will do a bunch of lines together so that they can make something that's complicated look like lines in real life. So polynomials, those are things that look like worms. And you can see that they're past the vertical line test and they're smooth and continuous. And exponential, that's things that look like this. Or they can look like that. And logarithmic, that looks kind of like this, a little bit different than exponential. Or the reverse, it can look like this. So these guys are smooth and continuous. Our low maintenance friends are smooth and continuous. And then our medium maintenance friends, things like rational functions, 1 over x. Things that, give us headaches on domain. Or, this little thing. Whatever. Things like that. Or radicals, square root of x. That's actually not too unfriendly, but, there's a domain question going on there. And then sort of this kind of thing. That's an example of a radical. So these guys, they have something weird going on. An undefined point, we have to be careful when we use them, because they can break computers. That's the end of the lesson.